Okay, so torsional oscillations are relatively slow transients when compared to rotor angle or frequency instability. So let's write the heading first: torsional oscillations. Torsional oscillations. They are relatively slow transients when compared to rotor angle or frequency instability. The oscillations with respect to rotor angle we have already seen. If a group of generators oscillate with another group of generators, they swing between themselves, then we have an oscillation with some frequency, or either it can be between a single machine and the whole system. I mean, against the whole system, a single machine swinging against the whole system. So these oscillations have some frequency. Compared to these oscillations, torsional oscillations have are slower. I mean, when compared to these oscillations, they are relatively slow transients. Now, till now, for studying the dynamics of the system, we assumed that the generator and the turbine, that is, this is considered as turbine generator, as a single mass. But in reality, this is a more complicated system, which means this is actually a group of masses.
Sir, I
Like
think
this.
that if we are writing anything, we are not able to see.
Oh, you are not able to see?
No, sir.
Okay, 1 minute. You just see the blank page.
No, sir. A torsional oscillation we can see, and this uh, T we can see. After that,
No, that's only that's the only thing I have written. This figure which I am drawing, you are able to see, right?
no, sir. That's what I'm saying.
Sir, one circle and above that T is written that
Now,
we can see.
now single.
Oh, I think it's a bit slow. That's why
Yes,
it's
sir.
Yes,
coming
sir.
now
Yes, sir.
only.
Yes,
Yeah,
sir.
delay is
Actually,
there.
Yes,
I have drawn 3 masses with 2 shafts.
No, sir. Not. We cannot see, sir.
Not visible. Okay, 1 minute. Let me
I think some delay is there.
maybe 1 minute. Let me see. Are you able to see now?
Yes, sir.
Yeah.
Now what you are drawing, we can see.
Okay. So in reality, we have multiple masses connected with a single shaft. So this can be different turbines. Suppose I am writing here turbine T1, turbine T2, and this is a generator. So this is a 3-mass system having 2 shafts. So in steady state or in equilibrium condition, or without the effect of a disturbance on any of these masses, they have the same speed. All these masses have the same speed, which is the synchronous speed of the generator. But whenever there is a disturbance, the disturbance can be from the mechanical side, or the electrical side. Which means if there is a disturbance from the electrical network side, which uh, causes a momentary speed variation in the generator. Suppose there is a momentary speed variation in the generator. That means basically electrical torque is what is the disturbance on the system, the whole system, the multi-mass system with shaft. So this will disturb the system so that if the shaft is not, the stiffness constant of the shaft, this K is the stiffness constant of the shaft. If it is not infinity, that means this is not this is prone to twisting, right? So these shafts are prone to twisting, and there may be small variations between the speeds of each of these masses. So earlier in equilibrium condition, we had all the speeds constant at the synchronous speed of the generator. But whenever there is a disturbance either from the electrical side or from the mechanical side, that is either from Tm or Te, that may cause a momentary variation in speed, and this will affect the torsion, the torsional character of the shaft. So it will have some amount of twisting. So because of this twisting, this is basically this is because of the different speeds of these masses. So this, now I am writing this as omega T1, omega T2 and omega G. These may be in different speeds for there may be a momentary speed variation. So now turbine generator system cannot be considered as a single mass with a specified inertia constant h. Rather, we consider them as different masses with different inertia constants. Now, so the torsion experienced by the turbine generator shafts are basically studied in this topic.
Sir?
Yeah.
Sorry, sir. Sorry to interrupt. I think there was some lag. What you told about K, sir? Stiffness?
Yeah, the stiffness constant. Actually, the shaft, if the shaft is ideally completely stiff, that means that any variation in speed for a particular mass will be directly transferred or translated to the other mass immediately without any delay. But if the shaft has a finite stiffness constant, not infinite, if the shaft has a finite stiffness constant, that means that the shaft is prone to twisting, or the shaft is prone to torsional oscillations. So this is like, let me open the video, 1 minute. I'll make it more clear. So we have, we have two shafts like this. In between there is a two masses. In between there is a shaft. So if the shaft is infinitesimally stiff, if it has infinite stiffness, then what happens is any variation in speed for this mass, that will be immediately translated to this mass also. So it will together rotate. So we can assume both the masses as a single mass. That is what we have considered till now. That is the turbine generator as a single mass. But in reality, we have different turbines: low pressure turbine, high pressure turbine, intermediate pressure turbine, connected by a single shaft. And all these turbines are connected further to a generator with the same mass, same shaft. So this is a multi-mass system. And in reality, we don't have infinite stiffness for the shaft. So whenever there is a disturbance at one mass, it is translated after some time only to the next mass. So there is a twisting happening in between twisting happening on the shaft. So this twisting can be in the form of an oscillation, and these oscillations can last for some time, and it will settle down later to again equilibrium, so that all the masses are in same speed. That is what is the concept.
Yes, sir.
Now, this variation in speed, or the disturbance to the entire system, the multi-mass system, this can happen from either electrical side or the mechanical side. Electrical side in the sense that the stator of the generator is connected to the electrical network. So any disturbance in the network can affect the speed of the machine, the synchronous machine, momentarily. So this may disturb the entire setup, and which may cause torsional oscillations, or the disturbance can be from the mechanical side, where the steam turbine is run because of the pressure of the steam. So that can be from that side. Now the oscillations are damped out. If the oscillations are damped out, we say that it's torsionally stable, right? Oscillations are damped out and it is again retaining another speed. All the masses are retaining a single speed. Then we call it as a torsionally stable system, or that disturbance which caused, that disturbance did not cause torsional instability, or rather if the input is a disturbance, okay, input to the system which disturbs the system is either from the TM or TE, mechanical torque or electrical torque. If this enhances the oscillations, enhances the torsional oscillations, which may cause breaking of the shaft itself because of the twisting effect, then we call it as torsionally unstable condition. Okay, so this is what we are going to study in this topic, the modeling of torsional oscillations and how the torsional oscillations, the dynamics of torsional oscillations can be studied using eigenvalue analysis.
Sir,
Yeah, tell me.
sir, let's suppose there is some torsional oscillation for a small period of time between T1 and T2 and between T2 and G, let's suppose.
Yeah.
So the adverse effects will be more in T2 and G, right?
That we cannot say. That is what actually we have to study the mode shapes. Mode shapes in the sense, what is this? 1 minute. Okay. We have to study the mode shapes of oscillations. To study mode shapes, we have to do some modal analysis. You might have already studied modal analysis in voltage stability. So we have to do modal analysis to understand which all shafts are most affected and which all shafts are less affected. That we have to see. From the, I mean, it depends on the disturbance, it depends on the masses, it depends on the hysteresis of the shaft. Several things are there. So we'll see that in detail. We'll see that. Now, let me. So what I'm writing here, you are not able to see. That is what you are saying. Okay, 1 minute. I'll
No,
do
sir.
one
Now
thing.
we can see.
You can see.
Earlier we were not able to see, but now we can see.
Okay. Now, so basically we have two modes of oscillations possible. One can be oscillatory mode. Second one can be common mode. Now, the oscillatory mode is the torsional oscillations and the twisting effect of the shaft, and it is more of localized in nature. That means each, the shaft between each mass or the shaft between two of the masses in the system, they have different pattern of oscillation. But common mode in the sense the whole system has an oscillatory nature with respect to the outside system. That means this is the whole system. I cannot change the color also. I don't know, some problem. This is the whole system. So the whole system is oscillating with respect to the connected electrical system. This is the connected electrical system. So as we had already considered the turbine generator mass as a single system, like that it has a common mode of oscillation. Inherently one common mode of oscillation is there. In addition to this common mode oscillation, we have shaft-wise oscillation, which is torsional oscillation. So this is oscillatory mode. The shaft-wise mode is the oscillatory mode, and this is the common mode. Now we are trying to analyze quantitatively the effect of oscillatory mode and common mode. Okay, now let's see. 1 minute. Okay, now okay, I'm going to draw the. I have a high pressure turbine, then an intermediate pressure turbine, then low pressure turbine B, low pressure turbine A connected to generator. So all these masses are connected. So this is a steam turbine generator system. The whole system is a multi-mass system. Now I am considering this as a first mass, this as a second mass, third, fourth, and fifth, with inertia constants H1, H2, H3, H4, and H5. Okay. Now it has different damping coefficients also. The damping coefficients are D1, D2, D3, D4 and D5. So when the blades are moving in the moving steam, there is some viscous damping. So that can be one reason for the damping. Another reason for damping can be from the generator rotor damper windings. So the generator rotor damper windings has an effect on the oscillatory damping, the damping of the oscillations that can affect all the masses because they are connected with the shaft. Now there is some damping from the electrical network as well. There can be some damping from the electrical network as well. How is that produced? Because there is an electrical torque that is developed by the generator G. This electrical torque depends on the total load that is contributed by this generator. If that load changes, there can be a momentary variation in the generator speed. So that may affect the whole system and that may cause some torsional oscillations. But if already there is a torsional oscillation and the electrical torque that is developed by the generator is such that it opposes the oscillations and it damps out the oscillations, then that can be one reason for the damping. It can be viscous damping, it can be because of the damper winding, it can be because of the electrical torque that is developed by the generator itself. And the effect of this electrical torque, the cause of this electrical torque can be from the electrical network because of the nature of the network. We'll see that how it will affect. Okay. Now, however, these dampings are of small magnitude. Now, K is considered as the torsional stiffness. The relationship between torque transmitted and the angular twist between the two ends of the shaft is given by T equals K theta. K is the torsional stiffness. So the torque that is transmitted from one mass to another mass can be quantified as K into theta, where theta is the twisting angle. Theta is the twisting angle. Now, if we want to measure or quantify theta, how can it be done? We know that for the generator already we have an angular measurement which is in terms of del. Right? What is del? Physically, what is del? It is a relative displacement, relative angular displacement between the physical rotor axis and the magnetically rotating or the synchronously rotating frame. So if that is del, when will this del be changed? Whenever there is a difference in, whenever there is a change in the difference between Tm and Te, that may cause Ta or Td, which is accelerating torque or decelerating torque. So because of this, del can change. So with respect to del, we are trying to measure the angular displacement of all these masses. So let us take like this. 1 minute. I don't know, it's a bit sluggish. Okay. Now this is a shaft. I have a mass here, which is some turbine. Then another shaft connected to the generator. This is the generator. Now, if this is mass 1 and this is mass 2, I am considering the torque transmitted as T12 and this is Te. The electrical torque developed is Te. Okay. Now, if there is a torsional oscillation or if there is a twisting that is happening, then T12 will be in this direction and another T12 will be in this direction. That is why this shift is happening. Right, because this mass is moving in a particular direction. Suppose that is in clockwise direction, and if it takes time to translate this torque to this mass, that means there is a twisting for this shaft. This shaft has no infinite stiffness. Its stiffness constant is finite. So there is a twisting on the shaft. Okay. Now I am considering the angle for both the masses. Let it be like this. This is omega naught, which is the synchronously rotating frame. Here also I have the synchronously rotating frame. Now this I am taking as del 1 and this I am taking as del 2, because now the displacements are different. If they are considered as a single mass, del 1 equals del 2. Otherwise del 1 and del 2 are different. So that is a concept here. Now the accelerating torque acting on the generator can be T12 minus TE, because T12 is basically Tm, the mechanical torque. So the accelerating torque is T12 minus TE, which is equal to the torsional stiffness constant of the shaft is K12 into what are the angles? What is the angular difference here? It was theta, but here what is the angular difference?
Delta.
Delta, but del 2 minus
Del 1.
del 1,
Del 1.
right? Del 2 minus del 1. Now this is T12. This is T12. Now we have to write TE minus TE, right? So minus TE. Okay, so this is the torque equation, accelerating torque equation. Now when we consider damping opposite to accelerating torque, we know that the damping effect is opposite to the accelerating torque. Therefore the equations of motion will become 2h1 into d delta omega 1 by dt, which is the, what is d delta omega 1 by dt, which is the speed deviation. Speed deviation in per unit, suppose, equals TA, which is basically coming from the swing equation. So TA, which is equal to K12 into del 2 minus del 1 minus TE minus D1 into delta omega 1. This is the damping torque, D1 into delta omega 1. Now what is d del 1 by dt? Equal to, this is the synchronous speed omega naught into delta omega 1, which is the change in speed. Okay, delta omega 1. Now the axis of generator rotor is displaced with the synchronously rotating frame by an angle del 1, right? Axis of turbine is displaced with the synchronously rotating frame by del 2, right? An angle del 2. Then this omega 1 equals omega 2 equals omega naught in equilibrium state or steady state, because there is no speed variation. There is no effect of disturbance. So when there is no effect of disturbance, all are running in the same speed, right? All are running in the same speed. But if there is a disturbance either from the TM side or TE side, there will be torsional oscillations. Now similarly we can write equations of motion for d delta omega 2 by dt and d del 2 by dt. Here we have written d delta omega 1 by dt and d del 1 by dt. So this is like, I'll take another color. Okay. Similarly, we can write equations for d delta omega 2 by dt and d del 2 by dt. So basically, how many state variables are here? How many state variables are here? I want some x dot, some state vector, rate of change of state vector x dot, where I have some state variables x1, x2, x3, x4 dot. Okay. So the entire system can be characterized by delta omega 1, del 1, delta omega 2, del 2. So if these are the state variables, if their dynamics could be represented in terms of x dot equals some ax, and if I am able to find the eigenvalues and eigenvectors of this Jacobian, the state matrix A, then we will be able to study the dynamics. We'll be able to do a qualitative study of the dynamics of the system. So that is what we are going to do. Now, um, now let's take an example. 1 minute. I'll stop sharing from this and I'll go to the lecture note. 1 minute. Okay. Okay. Are you able to see? Are you able to see?
Yes, sir. Yes.
Yes, sir.
Yeah. So, here. So we have taken the two masses like this. Then we are writing the torque equations, the accelerating torque equations, then the equations for omega and del, angular displacement and angular velocity. And we are considering the state variables as omega and del. So according to how many masses are there, according to the number of masses, the number of state variables will increase, and accordingly the order of the system will increase. Now, say we are given some values. The stiffness constant of the shaft between masses 1 and 2, K12 is given as 37.25 per unit, K23 is given, electrical torque is given 0.9 per unit, which is developed by the generator. Then the torque of high pressure turbine THP, we know that the high pressure turbine is here. See, HP, high pressure turbine, intermediate pressure, low pressure B, low pressure A, and generator. So this is the total, the whole system of steam turbine generator based power plant. Okay, so here when the generator is delivering 0.9 per unit power, the torques in intermediate pressure, low pressure B and low pressure A are 0.216, and in the high pressure turbine is 0.252. These are given. So this is just analysis of a result. Okay, so that is why these values are given. Now the angular twisting is del 2 minus del 1. We know that K12 into theta is T12, right? So del 2 minus del 1 can be written as T12 by K12. And under steady state condition, what is T12? That is TE itself, because all the torques are equally, equally transmitted, right? Equally and immediately transmitted. So the net accelerating torque is 0. There is no net accelerating torque. There is no disturbance. There is no effect of disturbance. The system is in equilibrium. Okay, so T12 can be written as TE. Now TE is given as 0.9 per unit. Now 0.9 divided by K12 is given as 37.25. This is equal to 0.0246 radians. So in steady state, right? In steady state, we have this del 2 minus del 1 as 0.0246 radians, right? Now T23. T23 can be written as T12 minus TLPA, because here, where is T23? T23. Okay, T12 is this, T12 minus TLPA, which is equal to T23. Okay, that is how the translation of torque happens. Now here, similarly, we are finding the values of del 3 minus del 2, which is 0.02185. Similarly, we can find all the values del 4 minus del 3, del 5 minus del 4, del 5 minus del 1. All these values we can find. Now, if you find del 5 minus del 1, what is that? The fifth mass is HP. First mass is generator. And if we find del 1 and del 5, if you find del 5 minus del 1, that is a net twisting. But the net twisting happens because of all these twists happening in each of the shafts. That is a net shifting, net twisting. Okay, so here the twisting between 4 and 3, twisting between 3 and 2, twisting between 2 and 1, and the net shifting between 1 and 5. All these could be found out if we know the stiffness constant K45, then the torque, because K into theta is torque. If our aim is to find theta from torque and K, that is what is our aim. Now we are going to get the linearized dynamic model. We are going to linearize this system, and we consider that the disturbances are very small. So we linearize the dynamical system around the nominal operating point. So we assume that a small disturbance in electrical torque happens from the equilibrium point T E naught. That is what is TE. TE equals TE naught plus delta TE. Okay. Similarly, for intermediate pressure turbine, low pressure turbine, all these torques at equilibrium is considered as TIP naught, TLPB naught, TLPA naught, etc. Similarly, for angular displacement, we consider that the equilibrium angle at equilibrium is del 10. So after a disturbance, it becomes del 10 plus delta del 1. Here also, the angle is del 2. After a disturbance, it becomes del 2 naught plus delta del 2. There is one, thing which I forgot to mention here. See, the angles cannot be equal. Okay. I think I mentioned that the angles can be equal here. In steady state here. See, the del 1 and del 2, these angles could be different in steady state also. Because see, once a twist is there, if it sustains with that particular twist, that means that there is an angular displacement here and here there is a different angular displacement, but it sustains in equilibrium state. This del 1 has no change, del 2 has no change. But whenever there is a disturbance, this del 1 will change, this del 2 will also change. But del 1 need not be equal to del 2. If del 1 equal to del 2, that means that this has infinite stiffness. The shaft has infinite stiffness. But that is not what is happening here. If there is a small twist and that twist sustains without oscillation, I am saying, if it sustains, then del 1 and del 2 could be different in steady state also. Okay, you got this point. Now, okay, now we are finding the torque transmitted. Finally, these are the, okay, as we have already written, this differential equation becomes 2h1 into d by dt of delta omega 1 equals k12 into delta del 2 minus delta del 1. These are perturbation models, because small change in angular displacement is only considered here. Small change in electrical torque is considered. Small change in angular velocity is considered. That is why this is a perturbation model. Okay, we are trying to linearize around the nominal operating region. So d by dt of delta del 1 and d by dt of delta omega 1. These are our state variables, delta omega and delta del 1. Similarly, for all masses, if we take, then it will become delta omega 2, delta del 2, delta omega 3, delta del 3. So how many state variables would be there for this system? We have how many masses are here and how many shafts are here. You see here, we have 5 masses, right? And how many shafts are there? 1, 2, 3, and 4. So how many state variables would be there? How many state variables? These omega and del should be written for all masses, right? So 5 into 2, right? So 10 state variables would be there. So we can find the state model of the system in terms of x dot equals ax, where x is a 10-dimensional vector. Okay, so that is what we are trying to find here. Delta omega 1, delta del 1, delta omega 2, delta del 2, etc. Delta omega 5, delta del 5. Whole transpose. This will be the state vector. Now we are trying to find x dot equals ax, and we are trying to find the eigenvalues and eigenvectors of the Jacobian, where the elements of A matrix will be in terms of stiffness constant K, inertia H, and damping D. Okay, K, H, and D. A matrix will be in terms of K, because this A matrix comes from these equations, right? D by dt of delta omega 1 is delta omega 1 dot. D by dt of delta omega 1 is delta omega 1 dot. Here d by dt of delta del 1 is delta del 1 dot. So if this 2h1 is taken to that side, then basically delta omega 1 dot is in terms of K, del, right, TE, etc. So that is what we are considering here, K, H, and D. Basically, these are the parameters, system parameters, which are contained in the elements of A matrix. Okay, now suppose we are going to study how the eigenvalues could be interpreted. Suppose we find the eigenvalues like this, plus or minus 10.12i, plus or minus 102.89i. Some values we are getting here, and we don't have a real part for this. All we have is the imaginary part only. Now we can find the natural frequency. How will you find the natural frequency? If this is omega, then this 10.12 is omega, then this is some sigma plus or minus omega I, and sigma is not there. It is not, in either of the eigenvalues we don't have sigma. We only have omega I, and omega by 2 pi will give you natural frequency, right? So if you do this omega by 2 pi, you will get the natural frequency 1.671, 16.37 hertz, 24.123 hertz, like that. So these are the 5 masses shaft torsional natural frequencies. These are the torsional frequencies of these masses. So these 4 are the torsional modes. These 4 are the torsional modes, and this is the common mode 1.671. Common mode in the sense you can see here that the common mode has a very low frequency. It is normally in terms of 2 hertz, around 2 hertz it will be. So this 1.671 gives you the common mode, and these are the torsional modes. And what are the torsional modes and common modes? Once again, I'll explain that. We have different masses, right? We have different masses, and between the masses there is a twist. So it is affected on the shaft, right? That is a torsional mode. And if all the 5 masses are considered as a single unit, and that is twisting with respect to the system that is connected with the whole group of masses are connected to another system, and there is an oscillation of the whole mass, as a single mass, as a center of inertia mass, it has an oscillation with against the system. So that is the common mode, and all other are torsional modes. How many shafts are there? 4 shafts are there, and 5 masses are there. So for 4 shafts, 4 frequencies, torsional frequencies should be there. That is what is shown as torsional modes here. Here, torsional modes. These 4 are the torsional modes. Now this is the common mode. Okay, so these frequencies we are getting. Now what will we do with these frequencies? What is the advantage of getting these frequencies? We'll see. We have to find the mode shape of torsional oscillations. What is mode shape? See, if we have oscillations in these 5 masses, say it can be like this. 2 masses are oscillating with respect to the other 3 masses. Such an oscillation can be there. Or the first 2 masses can have another oscillation like this. Or all the masses will have oscillation with the common system. So we have to basically decompose the whole oscillatory nature, the total oscillatory nature of the system, to a localized manner. In a localized manner, we have to analyze it. How many modes are there? Modes of oscillations are inherently there in the system. To find that, we need to draw the mode shape. How to draw the mode shape from the eigenvalue, we'll see. So now I'm taking the eigenvectors. From the eigenvalues, if I'm finding the eigenvector, I'm getting the eigenvector like this: minus 0.0117, 0.4346i. Like this, I am getting the eigenvector, and I'm finding the magnitude from the eigenvector. That is, magnitude of this is 0.4346, magnitude of this is 0.4452. Then each magnitude I am writing, and phase angle also I am finding 90 degree I am getting here. Okay, now with this I am going for drawing. I'm going to draw the mode shapes. Let's see how to draw the mode shapes. We may normalize the magnitudes with respect to the highest magnitude as 1. Where is the highest magnitude here? In these magnitudes, which is the highest magnitude? .4533. If this is considered as 1, we can normalize all these values based on the reference, this one. Right. So that is what we are doing. This 0.4346 is considered as 0.9588 because this is considered as 1. 0.4533 is considered as 1. So this 0.4356 becomes 0.9588. Similarly, for all these values we are normalizing, and the highest eigenvalue is considered as 1. Highest magnitude is considered as 1. Now we are going to draw the mode shape. How will you draw the mode shape? Let's see. So this is mode 0. We have different modes of oscillations in the same system same multi-mass system. This is mode 0 with 1.67 hertz. Where is 1.67 hertz? Here, the common mode. This is the common mode. These are the torsional modes. This is the common mode. Mode 0 is the common mode. Okay. Now let's see the mode shape here. Now we have three values: 0.996, 0.993, and 0.981. 0.996, 0.993, and 0.98 are there. Okay. So we are going to draw that here. These are the masses: 1, 2, 3, 4, 5. These are the masses. So the first mass, what is the 1? 1 is the normalized value. For the second mass, 0.996 is the normalized value. For the third mass, 0.993 is the normalized value. Like that we are drawing. And we don't see any negative values here. Okay, we don't have any negative values here. Since all the magnitudes are very near, all the state variables associated with this mode has more or less the same displacement. That is what is the meaning. All the state variables associated with this mode has but multiple modes are there. Okay, notice that multiple modes are there. This is just about mode 0 having a frequency 1.67. See, for any disturbance, any effect of disturbance, suppose you are considering a multi-machine system in which machines are oscillating against some other machines, some group of machines. This can happen in multiple modes in the power system. 1,000 machines are there. Some 50 machines are oscillating with another 50 machines in a particular manner. Some 60 machines are oscillating with another 60 machines in another manner. So all these are modes of oscillations at different frequencies. So we have to know all modes of oscillations, and whichever mode is prominent in the sense whichever mode has more amplitude. The displacement, the angular displacement is more for some modes. That means that the disturbance has affected more in that region. That means that region is prone to asynchronism, because basically these oscillations are in terms of del, power angle del, right? I'm not discussing about torsional oscillations. I'm discussing about multi-machine oscillations in the system itself, in the power system itself. Okay, similar to that only subsynchronous oscillations are modeled. So we have multiple machines oscillating in different modes. We need to know which mode is prominent at what frequency and what is the angular displacement. So if some modes are more prominent compared to other modes, we have to apply remedial measures in that region for near to those generators, or basically the control area, what we call it as control area. What is a control area? What is a control area? Anybody?
So control area where all the
two control areas connected by a tie line. What is the concept? A group of machines are in a particular control area. Another group of machines are in another control area. The frequencies can be different or same.
Same, sir.
same
Because it will be having same generation control, right?
No, in between there will be tie line power, a tie line.
That is what. In between there is a tie line power. So according to the direction of the tie line power, one region may be generating more power, and if there is a deficit, we can pump it to the other control area. That is the whole purpose of having a tie line. But what about the frequencies of the control areas? Delta F can be different in both the control areas. The change in frequencies can be different in both the control areas.
But all will be having same frequency, na, sir? Because they are having common generation control.
That is what. Actually, the control areas are differentiated based on frequency control. The ALFC droop characteristic for a particular control area could be different from another control area. Okay, we'll see that in the load frequency control. See, have you gone through the course operation control or system operation control?
Yes, sir.
Load frequency control is there.
In
Yes,
this
sir, yes,
semester, sir, yeah, we are doing, sir.
Okay. Load frequency control is over already. Anyway, in this course also we have load frequency control. I'll cover it after this. Okay. Let's not waste time. Here you just see this mode 0. So okay, this is mode 0. Now I'm going to coming to the second eigenvalue corresponding to the first torsional mode, 0 plus or minus 102.89 I, and the natural frequency is 16.37 Hertz. For this eigenvector is another eigenvector we are getting with respect to that mode. And with respect to that mode, we are again finding the magnitude and normalizing it, and we are finding the mode shape. Here, the mode shape you can see, two masses have magnitude more than 0, right? Magnitude in the sense here we have these two are minus 90 degree, these three are plus 90 degree. So that is why here these two are beyond this 0 point, and these three these three are below the 0 point. What this means is when these three masses are moving in a particular direction, these two masses are moving in the opposite direction. That means there is a mode of oscillation between these three these three masses against these two masses at a frequency 16.3 Hertz. That is what is the meaning. So this is one mode that is included in this oscillation. Three masses together having oscillations against two masses. That is also there. That is 16.3 Hertz oscillation. The other one is 1 point something, right? The first one was mode 0. This was mode 0, which was 1.67 Hertz. Now similar, so this is mode 1. Okay. Now similarly, we are going to find mode 2. Mode 2 is 24.1 Hertz oscillation. You can see the 24.1 Hertz oscillation here. I'll show you the 24.123 Hertz here. This is the 1.671 Hertz. This is mode 0. This is mode 1. This is mode 2. For mode 2, again, we are drawing the mode shape. So we are getting here like this 1, 2, 3 like this, then 4 here, 5 here. What is the meaning of this? How is the oscillation happening here? How is the oscillations happening? Can somebody interpret? When masses 1, 2, 3 and 5 are moving in a particular direction, either clockwise or anti-clockwise. Right, 1, 2 and 5, not 1, 2, 3 and 5, 1, 2 and 5 are moving in a particular direction. 3 and 4 are moving in a different direction. So that is another mode of oscillation. So all these modes of oscillations are included in the torsional oscillation that has happened because of the change in TE or development of TE of 0.9 per unit by the generator. All these values are given here. So with that, we are just interpreting the oscillations and mode shapes. So based on the mode shapes only, we normally based on the mode shapes of multi-machine stability. This is subsynchronous oscillation inside a turbine generator system itself. Similar to this, we can have multi-machine system in the power system. We can see the number of generators oscillating in a particular manner against some other number of generators. Based on that, we can place the power system stabilizer. We can find the location of power system stabilizer according to whichever mode is more prominent. So the displacement of here, you can see here it is written, the displacement of 4 and 5 masses with respect to displacement of masses 1 and 2 are in opposite direction. Okay. The displacement of 4 and 5 with respect to displacement of masses 1 and 2 are in opposite direction. Also 1 0 crossing is also seen here. 1 0 crossing is also seen. So because of the 0 crossing only, we say that these two are oscillating against these three. Okay. Similar to that, here these two are oscillating against these three, 1, 2 and 5, these three. So that is how we find two crossings are there. Two crossings are there. Okay, two crossings are there. So what is the meaning of two crossings? 2 0 crossings in the sense? How will the oscillations be? Here 1, 2 and 5 are moving in the same direction. 3 and 4 in a separate direction. But again, two types of oscillations are it is inclusive of two types of oscillations, because the direction is only decided by the the positive or negative side of 0. That decides only the direction of oscillation. But we have two types of oscillations inside. Swinging. Two types of swinging are there. Two machines are oscillating against 3. That is only one mode or one type of swinging. But this has two types of swinging because two zero crossings are there. Okay, two zero crossings are there. That means I'll tell you this 3, 4 are oscillating against 1, 2 in a different manner. 3, 4 are oscillating against 5 in a different manner, but 5, 1, 2 are oscillating in the same direction. At a particular time, we can see that 1, 2 and 5 are in the same direction. Okay. That is what masses 1 and 2 oscillate with respect to 3 and 4, and masses 3 and 4 oscillate with respect to 5. Masses 3 and 4 oscillate with respect to 5. Masses 1 and 2 oscillate with respect to 3 and 4. But the direction of 1, 2, the displacement of 1, 2 and 5 are in the same direction. Okay, that is what. So whenever the shafts are perturbed in 24.1 Hertz frequency, these modes will be seen. That is what is the meaning. 24.1 Hertz is the mode 2, right? So when the masses are disturbed at this frequency, 24.1 Hertz frequency, these modes of oscillations will be seen. When the masses are disturbed in 16.3 Hertz frequency, this is another torsional mode. This kind of mode shape or this kind of oscillation will be seen. Similar to this, if the masses are excited in 1.67 Hertz frequency, we have a common mode, mode 0. The whole mass, the turbine generator mass will oscillate against the system in such a manner. Okay, so that is what we see from the torsional oscillations. Okay, so you have lecture at 10:30, another lecture at 10:30?
Yes, sir. Yes, sir.
Okay, okay. So please go through this lecture note. I'll share this lecture note with you. Please go through it. It's just a qualitative analysis, but this is very helpful for analyzing the oscillatory stability of multi-machine system as well as turbine generator system. Okay, so I'm stopping the recording.